Hello everyone, I'm Jeff Rutan, a postdoctoral research assistant at Michigan State University for Dr. Kurt Steinke in soil fertility and nutrient management. And today I wanted to talk about 4R corn nitrogen management and specifically hone in on that rate component. Now in Michigan, split-in applications are a generally recommended best management practice for growers to improve their corn nitrogen recovery. Now I'm standing in the middle of one of our corn fertility studies that's around growth stage V5 to 6, which is a traditional time when many growers are considering side dressing their corn crop. But ultimately, growers must decide what is the right rate of nitrogen to apply and how do I determine that rate. Now, this rate is sometimes considered to be the economic optimum nitrogen rate, or the EONR, which is a nitrogen rate that produces a yield increase just large enough to pay for that last increment of nitrogen fertilizer applied. But the reason we fertilize is to account for what the soil cannot support the crop. However, soil spatial variability and temporal variation in the weather can affect soil nitrogen supply and corn response to nitrogen both year to year and among fields, which creates difficulty when trying to determine the optimum nitrogen rates. So today I wanted to discuss two models that we recently investigated, a preseason year-based model and an active crop sensor model, to help determine optimum corn nitrogen rates. The first model I want to talk about is a preseason year-based model, and that is the MRTN system, or the maximum return to nitrogen rate model. Now this is the current corn nitrogen rate recommendation model used in Michigan, as well as utilized by 7 Midwestern states. And this model is based on average corn yield response across many years and soil textures, and simultaneously accounts for grain and fertilizer investments. And this is a static nitrogen guideline model, meaning that it doesn't change during the course of the year. This model provides nitrogen rates based on corn response to nitrogen, crop rotation, soil productivity potential, and nitrogen fertilizer to corn price ratios. The way it works is assuming a linear increase in nitrogen costs, net returns will increase with grain yield until yield plateaus, at which point net returns diminish. The maximum return is the nitrogen rate producing the greatest return to nitrogen application. Growers are also able to fine-tune nitrogen rates within a profitable range of $1 per acre of the MRTN rate. Access to the MRTN table can be found online at our website at soil.msu.edu. Another model I would like to discuss is an active crop sensor model we recently investigated. Now, crop sensors will utilize an actively growing corn crop in order to determine the in-season side dress nitrogen rate. There are several sensors available on the market. As an example, I have the Green Seeker from Trimble. This particular model measures red NDVI, which is a 0 to 1 value, and lower values corresponding to less green biomass, which is an indication of plant vigor. Now, in general, active sensors will emit light from a source and then capture the amount of light that's reflected back off the target at specific wavelengths. Algorithms are then used to translate these readings into nitrogen rates. Some sensors require the establishment of a reference area within the field, which becomes the yardstick by which the rest of the field or the targeted corn is then measured against. Now, sensors and systems for translating data into nitrogen recommendations can vary by the vegetation indices used, the criteria for referencing healthy corn in order to gauge the vigor of your subsequent targeted corn crop, algorithms used for translating the data into nitrogen recommendations, and as also the growth stage that's associated with that specific sensor. Now, two things to keep in mind when using sensing-based technology in corn are these are not nitrogen sensors. So other nutrients such as K may reduce canopy greenness, so growers will want to ensure that the differences they are seeing are due to nitrogen. And another is other green biomass such as weeds may affect sensor readings, so you'll want to be up to date on your weed control. In a 2-year study recently conducted here at MSU and published in the Journal of Crop Improvement, models which included the MRTN and an active crop sensor model were used to determine corn nitrogen rates. Now, both of these models received 46 pounds of nitrogen per acre as a 2x2 at planting as 28% UAN. The MRTN model was side dressed at V4 while the active crop sensor model was side dressed at V8. Now, since Michigan does not have a published algorithm for crop sensors, a Minnesota-based algorithm was used to translate data into a nitrogen recommendation. Some key findings to come out of this study were: 1, weather variability impacted model-based nitrogen rates and subsequent yields. In year 1 versus year 2, the EUNR differed by 57 pounds of nitrogen per acre, which emphasizes that growers should consider addressing nitrogen rates each season instead of applying the same rate from year to year. In a wet year, that is, where cumulative May and June rainfall were above average, an active crop sensor model reduced side dress nitrogen rates, which decreased yields 8.7% relative to the MRTN model. However, when compared to a single urea application at planting of 250 pounds of nitrogen per acre, the MRTN model resulted in similar yields, but at 110 pounds of nitrogen per acre less, emphasizing the increased efficiency of a split application. Secondly, banding starter fertilizer at planting may have reduced expression of nitrogen deficiency at sensing time. Corn roots need time to adequately explore the root zone for available N and express nitrogen stress leading up to sensing. Using 46 pounds of nitrogen per acre in a 2x2 may have caused plants to appear more vigorous at sensing time and reduce the indication for fertilizer nitrogen needed further in season. The 2x2 placement is a strategy used to help corn start right to finish well here in Michigan, but may ultimately reduce the indication of nitrogen stress at sensing time, and further research is needed to validate algorithms when combined with early season corn nitrogen management strategies. For further information on other research, please visit our website at soil.msu.edu. Thank you.